This recording is only going to work the first problem in Chapter 14, Section 3, because in the interest of clarity, I want there to be a really clear step-by-step and understandable explanation of what's actually a rather complicated problem. So the problem that we have here wants us to use the following demand function. And for that demand function, we need to find the elasticity of demand in terms of Q. And so in order to do that, since what we have given to us here is actually the demand function, that is actually price. And price is equal to 400 times e to the negative 0.6 q. And in order for us to do anything with this problem, since we need to find dq dp, we're going to have to solve for p in terms of q. So that's what we're going to do first. So we're going to take the fact that p is equal to 400 times e to the negative 0.6 q, and we're going to solve that for q. So the first thing we need to do is divide both sides by 400, and that gives us p over 400 is equal to e to the negative 0.6 q. And then in order to do anything else with this, since we're trying to solve for q, we're going to use a property of logarithms that you may have forgotten about. And the version of it that we're going to use is the one that says that if you have a e raised to a power and you're trying to solve for the variable that's in the power, you can take the natural logarithm of both sides of this equation. And so we're going to do that. And now that we have that, we're going to take advantage of another property of logarithms that says that if you take the natural log of something that's raised to a power, then you can equivalently bring that power down in front. And so we bring negative 0.6 q down in front of the natural log of e. And that's equal to the natural log of p over 400. And then we're also going to take advantage of the fact that the natural logarithm of e, you can check this on your calculator, is equal to 1, and therefore it actually disappears in this problem. And so we're actually one step away from solving for q. So then what we're actually going to need to do next is to actually be able to solve for q. And in order to do that, I'm actually, even though it may seem odd, I'm going to change the negative 0.6 into a fraction. And negative 6 over 10 is negative 5 over 3. And that's times q because the natural log of e is gone now. It's disappeared. And then I'm going to multiply on both sides of the equation so that I can eliminate that fraction by negative 3 over 5. And I actually don't need that parenthesis, so we'll get rid of it. And so what happens here then is that 5 cancels into 5, and of course 3 cancels into 3, and negative times negative is positive, and so what I'm left with is q. And q is negative 3 over 5 times the natural logarithm of p over 400. And so now I'm ready to take the derivative of q. And the thing to remember here that's going to be a little troublesome is that I'm going to need to take the derivative of the natural log of a function of p. So I'm going to be needing to use chain rule. So the coefficient, negative 3/5, is just going to ride right along. The derivative of the natural logarithm of anything is 1 divided by whatever that is. Times the derivative of p over 400, and the derivative of p over 400 is 1 over 400. Because p over 400 is the same thing as 1 over 400 times p. And when you take its derivative, all you have left is its coefficient. So now we need a little bit of algebra magic. And so for that algebra magic, what we need to do is realize that 1 divided by p over 400 is the same as 1 times 400 over p. And so we have this. And once we have that, this is dq dp. And the 400s are going to cancel out. And so then when we multiply, dq dp is negative 3 times 1 is negative 3 over 5 times p is 5p. Or you can keep it as negative 3/5 times 1 over p, but it seems more logical, I think, to write it as negative 3 over 5p. So we now have the beginning of what we need to be able to find the elasticity of demand, which is E. And you need to remember that E is negative P over Q dQ dP. And so that's going to be negative P over Q times our derivative, negative 3 over 5P. And so what happens, conveniently, is that p's cancel out, and negative times negative becomes positive, and so then our value for E, or our expression for E, is 3 over 5Q. So actually doing the solution of D of Q for P was a lot messier in taking the derivative than actually finding E. So here's our expression for E, which is 3 over 5Q. And the other part we need to remember is that total revenue is maximized when E has unit elasticity, or when E equals 1. And the reason for that is because when your demand is inelastic, that means your revenue is increasing. And then your elasticity is actually the rate of change your elasticity is the rate of change in your revenue. So when E is greater than 1, then your demand is inelastic. I'm sorry, your demand is increasing. I'm using the wrong word. And when E is less than 1, your revenue is decreasing. And when E is equal to 1, your revenue is actually maximized. So we need to set equal to 1, E equal to 1, and that means that 3 over 5Q is going to be equal to 1. And of course, that's only going to happen if 3 and 5Q are equal to each other. And so 3 is equal to 5Q if Q is equal to 3 over 5. So the value of Q at which total revenue is maximized is 3/5. And that solves the first problem. And hopefully in a lot more clear and more understandable manner. So I will post this in Shobi, and the rest of the solutions to section 14, or chapter 14, section 3, will be in a separate video. But I wanted to do this one so that it would be very logical and step by step for you.